All right, welcome to your first set of notes, sections 1.1 to 1.3. We're going to do a little bit of review. This stuff you should have seen before. We're going to talk about variables and expressions, order of operations, how we simplify algebraic expressions, talk about the different number types, different number lines and subgroups of the number line, and do some preliminary work on simplifying. So by the end of this, you should be able to write an algebraic expression. You should be able to simplify expressions involving exponents. You should be able to use order of operations, and should be able to find a square root. And they're the standards that we're going to hit. Some vocabulary, and you're going to have a lot of vocabulary type questions on your tests, so you need to commit these to memory. First thing is a variable. A variable is a symbol, usually a letter, that represents the values of a variable quantity. Now, you never should use the same word to define itself. Basically, what this means is that it's a symbol or letter that represents the value of a number. Okay, it's a number, basically. Only, we don't know what that number is, and it's either because we don't want to know or we don't know yet, right? The most popular variable that we use is x. But we can use whatever. We can use p, we can use m, we can use whatever. And it doesn't have to be a letter. It could be a symbol. It could be anything. It could be, there are Greek letters that we use sometimes, sigma, theta. Any symbol would work. You can use cat, whatever. It doesn't really matter. But it's something that represents a number. An algebraic expression is a mathematical phrase that includes one or more variables. Now, I want to say a couple things about mathematical expressions. An example would be something like x plus 12. Okay, that has one variable in it. You can have more than one variable, and we'll take a look at those types of expressions later. But these are things that you do not have to solve. Inevitably, I get students who get something like x plus 12 as an expression, and they try to solve for x, or try to get x by itself. But there's no equal sign here. So we're not trying to figure out what x is, we're just trying to simplify down an expression. Now when we are solving equations, what we're going to do is we'll simplify either side of the equal sign, because either side of the equal sign will be an expression that we'll simplify. Okay, but if there's no equal sign, then we don't have to solve for anything, so we're not going to get any variable by itself. Next vocabulary term is an exponent. Tells you how many times to use the base as a factor. Some pretty fancy words there. Factor just means that the two things that are multiplied together. Factors are numbers or variables or whatever that are multiplied together. So basically, an exponent tells you how many times to multiply a base by itself. In this example, the 2 here is your base. That tells you what it is you're supposed to be multiplying by itself. This guy up here is your exponent. That will tell you how many times to multiply it by itself. So 2 to the 3rd power would mean 2 times 2 times 2, or 8. Or 2 cubed, another way to say it. Okay? A square root is our way of undoing an exponent. A squared exponent. Okay? Square root of a number is a value that when multiplied by itself gives the number inside the radical. For example, if I want to know what the square root of 4 is, I know the square root of 4 is 2, because 2 times 2 is 4. Square root means that we're looking for a number that when you multiply it by itself one time, you get the number inside the radical. So the square root of 4 is 2. Okay? All right. We need to be able to write algebraic expressions from verbal phrases or verbal sentences. Why do we need to do that? Well, it all goes back to why we're here. Can we get through life without algebra? Yes. Why are we here? We're here because if we can find a way to let algebra model particular situations for us, then it might make things easier to figure out. Might make values easier to find. So we want to learn how to translate verbal phrases and sentences into mathematical phrases and sentences. When we do that, we have to understand when we're supposed to be adding. And these are the words or phrases that you're going to watch out for to know that we're adding. Sum. Sum is the answer to an addition problem. If something says plus or increase, that means we're going to add. And then more than. More than is a phrase that you need to be careful of, right? More than. If I have 5 more pencils than you, if I have 5 pencils more than you, we can't begin to find out how many pencils I have until we know how many you have first, right? So if I said 5 more than, and since I don't know how many pencils you have, I'm going to let it be X. If I say 5 more than X, then I have to know what X is first, and then I'm going to add 5 to it. So I'm going to flip-flop the order here. Okay? Now, for addition, it doesn't make a whole lot of difference, but in subtraction, it does. And there is a phrase that's going to have us do that as well, flip-flop the order. Now, how do you know that you're going to be subtracting? If you see the word difference, minus, decreased, or if you see the phrase less than. If I have 5 pencils less than you, okay, then it's going to be the same thing as more than. 5 less than X. Well, I don't know how to figure out what 5 less than X is until I know what X is. I got to take X and then subtract 5 from it. So you have to flip-flop the order. Now in subtraction, the order does matter. And so X minus 5 is very different than 5 minus X. And so when you see the phrase less than, you definitely need to flip-flop the order. Okay? How do you know when you're supposed to be multiplying? If you see the words product, times, multiplied, or I'm going to add the word per in here. If you see the word per, then that's going to trigger multiplication for you as well, and I'll show you an example of that in a minute. Division. We know that we're going to be dividing if you see the word quotient, divided, or spread evenly, right? That kind of thing. And then we've got a couple more symbols that we know have verbal phrases that lead to them as well. And it's the less than symbol, which, you know, the alligator opening up to the right or the alligator opening up to the left is greater than or more than. And we're going to have to find a way to differentiate between these two. And we'll use context to do that. And the same thing for these two guys. Okay? Sometimes we're going to need the less than and greater than symbol. Sometimes we're just going to use addition and subtraction. We've got to figure that out. Now, let's write some mathematical statements from a verbal phrase. If we see a phrase, 4 plus a number x, well, that's easy enough. The word plus is in here. So we're just going to take 4 plus x. And that's it. Don't need to solve anything. Don't need to do any other work. We're just going to write a mathematical statement, an algebraic expression. 6 times a number y minus 3. 6 times a number y. If we take 6 times a variable or a number y, we just get 6y. Then minus 3 is just minus 3. And that's it. We're done. Okay? Now, you try it. Try number 3. It says 3 more than the quantity 5 times the number n. Try writing that. You can stop. You can pause the video, write down what you think it is, and then start it back up, and you can see if you're right. Okay, so what did you come up with? Well, hopefully you recognize the phrase more than. So we are going to add, but we're going to flip-flop the order. The 3 is going to come over here, and then this part is going to come to the front. The quantity 5 times a number n. 5 times n is just 5n. Over here. The word quantity sometimes triggers parentheses. We can certainly put parentheses around the 5n, but we don't need to, so we're not going to. But if you ever do see that word quantities, then that might trigger to you that you need to use parentheses. Just something to be watching out for. All right, try 4. Again, stop the video, start it back up, and see if you were able to get to the right expression. Okay, 2 less than. the sum of 6 and a number m. Again, there's that less than phrase. We're going to subtract, and then we're going to flip-flop the order. 2 comes over here, and the sum of 6 and the number m will come over here. Now here, since we have to take the sum of 6 and m, I am going to put those in parentheses. Because we've got to do this first before we can subtract 2. Okay? And the parentheses tell us the order in which we need to do things. Okay? All right. Speaking of the order in which we're supposed to do things, we need to talk about order of operations. And again, I know you've seen this, but we need to revisit it. Inevitably, students sort of lose track of what they're supposed to do and when trying to simplify algebraic expressions. Okay? Well, the first thing we got to do is clear up anything inside of grouping symbols. Now, what are grouping symbols? Grouping symbols can be things like parentheses, brackets, braces, even fraction bars are grouping symbols, because we can simplify the numerator and the denominator before we actually divide. And even something like a square root symbol is a grouping symbol, because we can work on the inside of that radical before we move on and do anything else. But we've got to simplify inside of grouping symbols first. Once we're finished with that, we can move on to simplifying exponents and roots. Once we've gotten through and multiplied out any exponents or worked out any roots, then we can look for multiplication and division. If there are a combination of operators like multiplication and division, if we got to multiply and divide and that kind of thing a couple of times in the same step, then we have to work left to right. We absolutely have to work left to right. And same thing with addition and subtraction. If there are a couple of different tasks involving addition and subtraction that we need to do, we need to work left to right, and we'll do that last. Okay? Now, I'm sure you remember, but there's an acronym that will help you remember this, and that's PEMDAS. If you need to, write that in the top of your homework papers or on your quizzes or tests, PEMDAS, which tells you to do parentheses first, then work on your exponents and roots, then do your multiplication and division, and then do your addition and subtraction. But you got to follow those steps. And this needs to be a thought process that you follow through on anytime you're simplifying. Okay, so let's try it out. Number 1, if we're using our thought process, PEMDAS, are there any parentheses we need to work on the inside of in this problem? The answer is no. So we're not going to worry about parentheses. What about exponents? Do you see any exponents? No. So let's move on. Do you see any multiplication or division? The answer is yes. There's a division and a multiplication, and so we have to work left to right. 30 divided by 5 is 6, and we have to do that first. Then we can multiply. 6 times 3 is 18, and there's nothing else to do, so we're finished. Now, the reason why we have to go left to right, if you choose to multiply 5 times 3 first, 5 times 3 is 15, and then 30 divided by 15 is 2. This is not 18, so it gives you a different answer, and as a matter of fact, it gives you a wrong answer. Okay, so you got to work left to right because the numbers that you get will change. Okay? All right. Okay, we'll talk about one more together, and then I'll let you work through a couple on your own. Okay? Now, you're probably missing these numbers. You need the 4 inside the radical, maybe even the 7 with the exponent, but make sure you fill in those missing numbers. Okay? So, PEMDAS. Do you see any grouping symbols? Do you see any parentheses? I do not. The radical can be a grouping symbol, but there's just a 4 inside of there. There's nothing that we can simplify with that. So we're good here. Do you see any exponents or roots? And I do. I see an exponent here, and I see a root here. So I can take care of each of those in this step. The square root of 4 is 2. 7 squared is 49. And we can do those two operations and then rewrite. So now we're done. Multiplication, division. Okay, well, remember that we're sort of working in the grouping symbol right now with the fraction bar. We're simplifying the numerator, and then we're simplifying the denominator. There's multiplication in the numerator. 7 times 2 is 14. But there's not any multiplication or division in the denominator. So we move on. In the denominator, we have addition and subtraction. Now remember, you have to go left to right. So 8 plus 49 is 57. 57 minus 1 is 56. Now we have 14 over 56, where we can divide that out if we wanted to, but more often we're going to want to just simplify these fractions and get 1 over 4. Okay? So be careful. If you need to, do one step at a time and just rewrite. All right? Here's 3. Try 3. 1/3 times 9 times 3. 1/3 times the quantity, 9 times 3, plus 18. Try that. Stop the video. Give it a shot. If you're wrong, it's okay. Start the video back up. See if you are, and then change it if you're wrong. Okay. How'd you do? Got to do PEMDAS. Parentheses first. And I see inside the parentheses I got 9 times 3, and we've got to multiply that out first and get 27. That's done. I don't see any exponents. I don't see any roots. So move on. Multiplication and division. I see multiplication right here. Even though it involves a fraction and you're not going to want to do it first, you have to do that before you add the 18. 1/3 of 27. So you can multiply 1/3 times 27. You get 1 times 27, which is 27. 3 times 1, which is 3. 27 divided by 3 now, we got to do the division now, is 9. 9 plus 18 gets you 27. So hopefully you got 27. Okay? One more for you here. Again, stop the video, try that out, and see what you come up with. Sorry there. Anyway, you should come up with 17, and here's how. So if you're not coming up with those, make sure you do get the help you need. Come see me during STAR or after school or sometime, okay? All right. Now, evaluating algebraic expressions, right? Like I said, we use a variable when we don't know what a number is, and it's either because we don't want to know or we haven't figured it out yet. But we leave a variable in there so that we can open up possibilities to different values. So in the algebraic expression, 3x squared plus 1, this 3x squared plus 1 stands for a number. We just don't know what that number is because we don't know what x is. So what we want to know now is, what is that number if x is 4? Well, to find that out, we're simply going to plug 4 in for x here. When we do, we get 3 times 4 squared plus 1. 4 squared is 16. You got to do that first, right? You got to do your exponents first, inside parentheses first. Then you got to multiply. 3 times 16 is 48, plus 1 is 49. So you plug the number in for the variable, and then you just go back to your order of operations. Okay? Let's evaluate this expression when x is -2. Stop the video, give it a shot, start it back up, and see what you come up with. Did you get 7? So we're going to plug in -2 for x. And now, PEMDAS says we have to do exponents first. -2 squared is -2 times -2. -2 times -2 is +4. right? Then we've got 32 divided by 4 minus 1. You cannot do 4 minus 1 first. Even though it's easier and you're going to want to, you can't do it. Division has to come first. So 32 divided by 4 is 8. 8 minus 1 is 7. Okay? That's where 7 came from. You got another one. Try 7. Again, stop the video, see what you come up with. Make sure you follow your order of operations. And so hopefully you got negative 180. Okay, if not, come find help. Let's figure out why you didn't get negative 180. Okay? All right. Now, we're going to step this up a little bit and start talking about how to write equations. Again, I said, if you can find a way to let algebra model a situation, then maybe it could be easier to find out something that you're trying to figure out. So, in this situation here, you and your friends are having lunch. The lunch costs $2 per plate. The waiter gives a bill for $25.20, which includes tax of $1.20. Write an equation to model this situation. Don't have to worry about solving the problem. And I think you're missing the 25-20 in your notes. Okay, we're not going to solve, but we are going to write an equation. So here's what we know. We know that everything totaled $25.20. That's what everything has to equal. The cost has to equal $25.20. Where does that cost come from? Well, here's that word per. We know that the lunch was $2 per plate. If there were 10 plates at $2 per plate, how much money is that? Well, hopefully you're thinking it's $20. And it would be because we take 10 times 2. So the question becomes, did we know that there were 10 plates? And the answer is no. We don't know how many plates there are. So what are we going to let that be? The number of plates we can let be x. And once you decide what variable you're going to let it be, then tell the world. X is the number of plates. You have to define your variables. So if x is the number of plates, we know that if we take the number of plates times 2, that will give us the cost of the plates. So 2 times x is just 2x. That's not all. That's not the only place the cost came from. It also came from $1.20 in tax. So we have to add $1.20, and that's where we get our total cost of $25.20. There's your equation. We don't have to worry about solving it yet. We'll do that some other time. Okay? All right. Try 9. See if you can't come up with an equation from this situation. I'll show you what you should have come up with, and if there's issues getting there, make sure you come see me. And hopefully you came up with this. C is the number of cars sold. We don't know how many cars the salesman sold last month. But we know that every time he sells a car, he makes $375. And there's that word per again. So since C is the number of cars, and he makes $375 for every car he sells, then we can take, just like the $2 per plate before, we take the 375 and multiply it by C to tell us how much he made off of selling cars. Now, that's not the only place where his income is created. He gets an automatic $900 just for showing up. So we figure out how much he makes off the cars, and then we got to add in the $900 to get your total of $4,650. Again, we don't have to worry about solving this. We're just setting up our models right now. Okay? All right. The number line. Numbers were invented. Number lines were invented. Groups of numbers were invented all along the way because we kept creating or kept finding needs for different numbers. We started off way before we could even write on walls. We started off with the natural numbers. Those were the numbers we used to count. If I wanted to count my sheep, I would start with 1. 1, 2, 3, 4, so on and so forth. Then we started writing on walls and recognized that we needed to have a placeholder. We needed to have a number that would be a placeholder. And so that number was 0. So we created the whole numbers, which was the natural numbers, and then just added 0 in there. Then we started performing operations, addition, subtraction, that kind of thing. And negative numbers became a way for us to represent subtraction. So we needed more numbers. And so we created the integers, which are both the positive and negative whole numbers. No fractions yet, just whole numbers. We didn't get fractions until we started dividing things. Once we approached dividing as an operator, we realized that, yes, sometimes numbers divided out to whole numbers, but sometimes they didn't. And so they created what are called rational numbers. A rational number is any number that can be written as a fraction. Okay? Now, every fraction is not necessarily a rational number. If you take the circumference of a circle and divide it by 2 times the radius of that circle, or if you take the circumference of a circle and divide it by the diameter, you get some number that you cannot write as a fraction. That number is pi, by the way. And so now we started coming up with these other numbers that didn't fit into any of these other 4 categories. We created what are called irrational. Created what are called irrational numbers. And these are numbers that cannot be written as a fraction. Pi is the most famous of those numbers. There is an exponential variable called e that you will be exposed to. Okay, but there are other irrational numbers out there as well. But those numbers cannot be written as a fraction, right? All right. Now, a number can belong to more than one group, number group, right? The number 9 would be an integer because it's a positive whole number. It would also qualify as a whole number because it's a whole number. And it could also qualify as a natural number because it's a number used to count. Okay? Wherever the number falls in this ladder, it will satisfy every subgroup under it. You can go down, but you can't go up, right? So that might be a trick in trying to figure out what subgroup this number is going to belong to. A number is going to belong to. Now, if it belongs to a number group over here, it's not going to be irrational. And if it's an irrational number, it's not going to belong over here with these guys. Okay? So, some numbers here. What subsets of the real numbers do each number belong to? Well, if we back up, -5. -5 is definitely an integer because it's a negative whole number. But because it starts here, it's going to belong to every subgroup under that. So it's going to be a whole number and a natural number. So this guy is an integer, a whole number, and a natural number. Okay? Pi, I've already said, is an irrational number and cannot belong to any other subgroup. Okay? Try to figure out the next 4. And I'll show you those and see if you're right. Okay, so I just realized that I told you completely wrong. So we need to go back up and take care of that. Okay? If a number falls in these subgroups, then it will fall into the group above it as well, group or groups above it, but not necessarily below it. For example, -5 for our first one is definitely an integer. It's a negative whole number. We can write it as a rational number by putting it over 1, but it will not fit into the whole numbers and the natural numbers. They don't belong there. Okay? So we can go up, we just can't go down. Okay? So I apologize for that. Make sure that you make that mental note and you fix that. Okay? So, -5 would be a rational number and an integer. It's a negative whole number, so it's definitely an integer, and so we go up into a rational number. Pi is irrational. 4,328 is a number that we can count with, and so it starts in the natural numbers and works its way all the way up into whole, integer, and rational. Square root of 17 is irrational. Right? 3/5 definitely fits into the rational, but is not an integer. It's not a whole number, and it's not a natural number. It's just rational. The same thing with 0.3 repeating. We can write it as a fraction, but it's not going to be an integer, it's not going to be a natural number, it's not going to be a whole number. Okay? We can work our way up, we just can't work our way down. Okay? So I apologize, make sure you do get that fixed in your head. Some more vocabulary for you. The distributive property. The distributive property says that if we have a number sitting outside of a set of parentheses, then we can distribute that to the numbers inside. So A times the quantity B plus or B minus C, it's just A times B plus A times C, or A times B minus A times C. And all this is saying is it doesn't matter if the A is in the front or in the back, we're still going to distribute. A term. A term is a number, a variable, or the product of a number and one or more variables. So they're basically the things that are in between the plus and minus signs, all of our operator signs. That's a term, that's a term, that whole thing's a term, that whole thing's a term. A constant is a term that has no variable. It's just a number. It's constantly the same value. A coefficient is the number in front of a variable, basically. It's the numerical factor of a term. It's the number in front of the variable. So for 72b, 72 is the coefficient. Like terms. These are terms that have the same variable factors. You have to have the exact same variables. The same variables and the same exponents, but we'll worry about exponents later. So 3a and 8a are like terms. 4xy, 9xy are like terms. Okay? So, we can apply some of these different principles. Number one here, 5 times x plus 7. We're just going to distribute this 5. 5 times x is 5x. 5 times 7 is 35. Okay? Try this guy and see what you come up with. Just distribute, you get negative 6b plus 14. What's going to happen here? There's really a 1 out front, right? So distribute, distribute. We get negative 4y plus 5. Negative 1 times 4y is negative 4y. Negative 1 times negative 5 is positive 5. What happens here? We end up with positive 21 plus 5m when we distribute that negative. Okay. All right. Like terms. We want to be able to simplify. When we simplify, we combine like terms. No equal sign. So we're not moving anything across equal signs. We're just going to take this guy and combine them or add them or however you want to look at it. But we've got to take 3x and negative 5x and combine them and get negative 2x. And then we're going to have 8 and 6 that we're going to add together and get 14. And so now we're simplified. Negative 2x and 14 are not like terms because they do not have the same variable. Okay? Number 6. Your like terms are 16x squared and negative x squared. And when you combine those, you get 15x squared. You're basically adding 16 and negative 1. And then you've got 8x and negative 4x, which when you combine, 8 plus negative 4 is positive 4. And then you've got 7 plus 2, which is 9. No more like terms. We're done. Okay, now we're going to combine a few things. Here first, I've got this 4 outside the parentheses, and we want to distribute first. 4 times x is 4x. 4 times negative 8 is negative 32. And then we got to combine like terms. Here's a like term, here's a like term to get 13x. Here's a like term, here's a like term. Negative 32 plus 5 is negative 27. No more like terms, and so we're done. Okay? Try this one, see what you come up with. Stop the video, start it back up, and see if you're right. And so you should have just gotten x. Distribute the negative, combine your like terms, and you end up with just x. Okay? All right? If you weren't able to get that, make sure you come see me during STAR or after school, and we'll get you ironed out. And that's it. It's a lot of stuff, but it's a lot of review. Hopefully it makes enough sense. Get your homework done by next class, and we'll see you then.